Good morning, Sawadee Krap, everybody. It's my pleasure to be here again. And today I'm going to share with you from the scientific viewpoint some more information on is Bangkok going to become an underwater city, and how the situation looks right now. And actually, there's a title behind that and that work, and that involves the monitoring of the tectonic and man, so human-induced land subsides in Bangkok, Thailand, using geodetic space and ground data. So I will explain you what techniques we have been using. And I'm presenting this, of course, myself, my work, but also with my colleague, Mark Naye. He's also been previously here in Thailand, giving talks on our work. And of course, we have cooperation. I have to mention many times that the results today I present would not be possible without the good cooperation we have with a number of universities and government agencies in Thailand. And some of them already go back to 2000, so almost 20 years ago. Okay, today, the contents of the talk. First, a brief introduction, although some of you already know about my university, Delft University of Technology in the Netherlands. Then the research activities we have been undertaking all those years. Then I will get into a description of the geodetic techniques we are using to study the sea level change, not only in Thailand, but of course today we focus on Bangkok. And then also important there is actually vertical land motion comes into play there. That's a small sidestep, but that has also something to do with the big earthquake. And that also creates some additional motion in the vertical direction. Okay, of course, the significance, how important is this data, those motions we have seen from the scientific results. And then I'll show you a study case we have completed already, and that's on the vertical motions in Phuket. So it's very similar than Bangkok, with the exception that Phuket is an island, a rocky island, and there is not so much subsidence due to sand layers, which are going down if there's a change in the groundwater level. So actually the Phuket study is more easy because we only have to take into account vertical motion due to tectonic and not due to human-induced or groundwater extraction or changing levels and sand compacting in a big city like Bangkok. Okay, so now we have a look at a past to present relative sea level situation. I say relative. Why relative? Because if I'm standing here and I'm not moving and the sea is coming up, I see, of course, how much the sea is rising. But if at the same time the land below me is going down, so the sea will go up even much more. So we always talk in these studies about relative sea level. So you have an absolute sea level, which means how much the sea is increasing. But on the other side, you also have to know if the land on what you are standing is moving or not vertically. If that's the case, then you will see much more sea going up actually because you are going down. So that's an important one. Then also, I'll show you some recent results from four techniques. I will describe them. They're satellite altimetry, tide gauges, interferometric SAR aperture radar. That's a satellite altimetry also using a satellite. And of course, GNSS, or most of you probably know it much better as GPS. GPS is the oldest of the global navigation satellite system, the longest running one. Actually, most of the data we are using from the past is all GPS data, because back then only the GPS system existed. Nowadays, we also have the Chinese Baidu, we have the Russian GLONASS already, and also the European, where I come from, we have the Galileo system, so we can even track more. But that's just why nowadays we say GNSS, because that's the family name for all the global navigation satellite systems like GPS. Also, I will come into look at what's the possible causes for the progressive land loss and flooding in Bangkok. And also, I will show you some relative sea level rise scenario That's a scenario based on scientific data and what would happen if no countermeasures would be made. Then I will show you what will happen to Bangkok and the surrounding region. Of course, it's not going to be for tomorrow, but you have to think in the future, decades or century. If you don't do anything, then Bangkok indeed might become an underwater city. But of course, we can prevent that happening. And of course, conclusions and outlook will finish my talk. So TU Delft itself is a university. I think it's pretty well known. We're a technical university, and myself, there's many faculties. Myself, I'm actually working at the Astrodynamics and Space Missions chair, and in the past, long time ago, we were also well known as the Delft Institute for Earth-Oriented Space Research of DEOS. That's actually in Southeast Asia. I think from previous project we are well known. So it already says something about what we are doing. We're using space data to look at the Earth. And yeah, the department, and then actually my faculty is aerospace engineering, because the GPS satellites, that's actually my work, and my colleague is using the other satellites. That's of course is aerospace, and then our research is more application of the data. And we ourselves have been present and working in Southeast Asia. This is all research since 1994, where we had the first big project, Southeast Asian project. And we're using all those techniques, which I will get into more detail later on, to study mainly tectonic motion, deformation, sea level rise, and land subsidence. And of course, I mentioned to you already before, we have, not only in Thailand, but also in Malaysia, Indonesia, we have already long-standing cooperations. So for the past, quickly, what we have done, we have participated in this first project, and then later on, we have, in Thailand, been doing more work. And actually, we have asked, in that case, also the Royal Thai Survey Department to remeasure some GPS points. That's just a reference benchmark, which you can put a GPS or GNSS antenna and measure, because you need actually a lot of data over a long period of time to say something useful, especially in the vertical direction. We had a couple of human resource development and common applied research projects together with Chulalongkorn University and also the Royal Thai Survey Department. I already mentioned to you, and you see the years. And we also installed some equipment in Thailand still, and yeah, then it involves, of course, data processing scientifically to get maximum results on deformations, and we had a number of publications, I think, also on the big earthquake in the past. And also through the years, actually, the relevance of our work of the vertical motion detected by GNSS, here I mentioned GPS still, for sea level rise. And yeah, and also there important is GPS or GNSS again, data sharing. You need a lot of data, and many government agencies or even universities are operating stations, either not only GNSS, but can also be another one. And it's really important to collect as much data, and I think it's the best way to do it is to work together and share the data among each other, so everybody benefits. This quickly shows us the past projects. I think we call this Geo2TechD. D in Thai, of course, means good. So this was already a cooperation project we had. We had another one together with universities and government agencies in Thailand, Indonesia, and Malaysia. Okay. So right now, what we are still doing is that we're still operating, among others, 4 of those continuous, so they measure the whole time, day in, day out, GNSS stations in Thailand. We still have cooperation, although it depends on funding from projects, but we always try to continue even, as we call it, as a scientific hobby, so to ensure that we keep on doing our research. Of course, if we have a big project, we can do more and involve more people. Okay, and then important there, I think that's my own work, is to try to get those very long, we call it time series. So that means you have over 10, 20 years, you have measured with GPS the same location, and then you can see over this very long time period how it moves, both horizontally and vertical. And of course, the vertical is what we're today interested in. And yeah, and this vertical work, especially Phuket, we already did some work. Bangkok, we are also working on. I show you, but there's still more work to do. we have been using for our research to come up with today, hopefully some useful results. So the techniques I already mentioned to you, the theme already, okay, I mentioned to you what we study, so tectonic motion, but sea level change due to global warming, and land subsidence, which is mostly related to the groundwater level changing in an area. The techniques we have available is as I mentioned to you, the Global Navigation Satellite System, GNSS, satellite altimetry. I will just call it SALT for now because it saves some time in the next sheets. And then this difficult word, interferometric synthetic aperture radar, INSAR. This is also a satellite making radar measurements. And that's the same for the satellite altimetry, of course. And then we have the tide gauges, which are, of course, not on space. They are just on land around the coastal regions, and they measure the variation on a continuous or per hour basis of the sea level. So you have, of course, the tides going up, going down, but over many, many years, you can also see something about what the sea is doing, if it's going up or going down. And here, just to illustrate you what all these techniques can come up with. This is a result within the past, is about the motions of Southeast Asia. I think the Southeast Asia was moving around 3 centimeters per year to the east, but everybody is moving to the east-southeast, but everybody is moving together, so you will not notice anything about that until, of course, we had the big earthquake. Satellite altimetry tells you something about the height of the sea, and we can do that, of course, globally with the satellites, so it can show you what is going on in the seas over a period of time. The earliest satellites were launched, I think, beginning the year the 19th, I think. So from 1992, we can use satellites also to look what the sea is doing. Then INSAR, that is another technique which you can look at how things are moving, but in the same picture. So it means relative. So one point is 0, for example, then things can move up or down, but it's all relative to 1 point. So it's a relative measurement. If everything is moving up at the same rate, like 2 centimeters per year up or down, you of course will not see that. You only see the relative differences. And of course a tide gauge, if done properly, it measures what the sea is doing. And here you see a result going back to 1880, because tide gauges exist for a long time. And even if you cannot see the numbers, you can clearly see that the sea has been rising for quite some time already, but especially in the last period, you can actually see that the line is going steeper up. Okay, and all those techniques, actually the GNSS can help us to do something extra with our measurements, because I told you this is relatively, so if you measure GNSS is an absolute measurement technique, so it measures the absolute motion of any point on Earth in 3D directions. Now, if you do that for a point in this field, then of course you can make this relative to absolute. A tide gauge itself can also be moving. I will come to that. So it may be moving up or down because the land is sinking. Most of the time the land is going down. If you measure that with GNSS at the location of the tide gauge, then you can correct for that, and then you can again make this relative to absolute conversions. And the same applies actually for satellite altimetry. If you know what the satellite altimetry is, an absolute measurement of the sea level is doing, and you measure with GNSS what your station on the coastal region is doing, then you can know how much the sea is coming higher or lower, depending if you or the station is moving up or down. So GNSS is actually very interesting to connect all those different techniques. So if we look at Bangkok, so this should look a little bit like Bangkok, and you can already see how all these techniques come into play. First, we have the satellite altimeter. So this is the satellite flying over the Earth, and when it's over the ocean, it will send out a radar signal, bounces back. Just to keep it simple, these travel up and down. Radar signals travel around the speed of light. So you can measure, if you know where your satellite is, you can measure how long it takes to go down and up. And from that, you can see changes, or you can know the absolute height of the sea. A tide gauge, as I mentioned to you before, is fixed to the land, and it measures either old-fashioned way in a pipe, and then there's a floating device moving up or down, connected with a cable, or you can also use a radar or even acoustic, but it comes down to the same. You measure the distance from your tide gauge to the sea level. Then we have the GNSS stations. They're actually just receiving signals. This is just to illustrate you, there are many different GNSS systems. So there are actually, per system, 24 to 30 satellites. But just to show you how the idea works, is that the GNSS station is just measuring the signals from the satellites. And again, the signal travels over a certain distance with the speed of light. The satellite, we know, it tells you where it is and when it sends the signal, and the receiver measures when the signal arrives. So again, you can calculate a distance, and if you have a distance to a number of satellites, actually the minimum is 4, 3 for the position, and 1 because the receiver clock, which measures the time, because the satellites, they use actually atomic clocks, but a receiver cannot use that because it would become too big. So we have to also correct for the clock error of the receiver. So with minimum 4 satellites, you could do that. But that's not the best. In general, you can get 10, 11, 12 satellites from one system all the time you can measure. So that's on land. This is on land. The tide gauge is on land. The GNS stations are on land. And then, of course, we have the other technique, satellite SAR. And that's, again, a radar. But this one is not now this time looking at the sea, but it's looking at the land, and it's sending out a radar signal, and the radar signal is bouncing back. And by doing that, of course, this you can do globally while you're traveling, and here they make an image, can be 30 by 60 kilometer when the radar is on, and they collect this data, and then when it comes again, you can see if anything changes in that image. So with these techniques, we can measure the subsidence, and with satellite altimetry in the tide gauge, we can measure sea level rise, or maybe I should say correctly, sea level change. And of course, as I mentioned, if the city is going down quicker because something is going on with the sand or the sediment layers below it, and the sea is actually already going up. We all know the sea is going up anyway because of the global warming. We don't have to discuss if global warming is created by people or not. There's some big discussion about that, but it's just a fact. Global warming is occurring, and even if it would be by nature, it is a fact that it's occurring, so we have to do something about it. So the whole discussion is humans or not, or exhaust, that's for scientific, for me, it doesn't matter. I only know that we measure clearly that the sea is going up, and we have to do something about it. If not, we will get problems, especially all those coastal regions where the land is quite low and going up only slowly. If you have a mountain, or like the Phuket, you have the mountains, the hills, so you go up from the sea quickly. You have not big problems. But in Bangkok, you have this long, flat plain, and it's only going up a couple meters over a couple 100 kilometers. So you can imagine if the sea is going up and part of the land are going down, the impact on the city is going to be much bigger. And nowadays, many more people living in the coastal areas also, so they will notice quickly. And again, here I mentioned you the term the relative sea level. So that means how much the sea is going up with respect to the land, which can also go up, but that doesn't happen a lot. It does happen in the Himalaya, Mount Everest, because of collision of continental plates, but of course that's not happening in Thailand. So mostly if the land, and the layer is very thick, the sand layer is up to 2 kilometers below Bangkok. So anything in the sand going on will have an effect on how the city is moving. And if the sea is going up, yeah, then you get a bigger effect. Okay, so GNSS, we can use it to measure the absolute vertical. I say vertical, it measures also the horizontal, but today we are interested in vertical land motion studies. And then, as I mentioned to you before, we use scientific equipment. You also have it all in your phone, but your phone you can get 3-4 meter accuracy maximum. We can actually get millimeter accurate, but we have to do the processing later on, so we cannot do that in real time. And with that, of course, you can compute position anywhere on Earth. Now, let's say the position is in Bangkok, and the changes in the position over time give you displacements or velocities. Velocities we mostly refer to when it's not changing over a long time, and displacements we tell more is a velocity which is not behaving linearly. So that's the GNSS. It can give you this vertical motion. Now let's look at satellite altimetry. It can give you absolute sea level change for use in studies. So, of course, what it measures itself is the mean sea surface. And actually here we see that it looks like the relief of the sea bottom, but that has to do with gravity. When there's more mass, then the water is attracted more, and when there's less mass below, or the rocks, you have a mountain below, or you have a very deep valley in the ocean, then of course the water is going to follow that due to gravity changes, and the satellite will measure that. Of course, there's also the yearly variability, for example, here because of the jet stream. So that's changes you can see from within a year. But we are mostly interested in the changes over a long period of time, so the average or the trend. And you can see that here, actually, the trend which is calculated from using the satellites from early in 1992. And I think the global rate is 3.2 plus minus. So it can always be 0.4 higher or 0.4 millimeter per year lower. That's the trend we can get from the satellites. The nice thing about satellites is they measure everywhere, so you can easily get anywhere on Earth, you can measure that. This is the global average, but you can also measure, for example, in the Gulf of Thailand. I'll show you later. Then the tide gauges, they go back much longer, and actually the red here is this small period now. Well, it's not small, but compared to human life, or the life of the Earth itself, of course, it's a small period of time. It's almost like only 20 years. The tide gauge itself go back longer from the starting somewhere in the 19th century, 1880. But you can see they measure. But of course, they have a much bigger an accuracy than the satellite. The satellite can measure more accurately. But what you can see is for a long time already, there has been a period going on from where the sea is going, appears to be going globally up. But in the last part, you can see it has become more steep. I mean, this is no material to discuss. You can find in many places this actually results. We can calculate ourselves, but this was done by the Americans, but they all use the data from the same satellites. And all those numbers are the same. So the 3-point-something millimeter per year average over this period, so it can even be more in the last years, everybody knows that's occurring. Why? Okay, that's a discussion I'm not going into, because at the end it's what you want to do with it. Okay, then the tide gauge itself, it can measure the relative sea level change. So the tide gauge is located, here it's the tide gauge at the Naval Dockyard in Bangkok. It's located on a pier, and it's measuring the water level. Actually there's a plastic tube going, but there's also a radar they're using to bounce a signal down, and it reflects from the water. And it registers continuously per minute this change of the sea. So the tide gauge itself, of course, can also move. And yeah, of the post-glacial rebound, that means when there has been a big glacier period, or you know, like 10,000 years ago, there was a period where there was much more ice everywhere, and that ice has melted, so the land even nowadays is moving up. But there also been tectonic uplift that has to do with the movement of the tectonic plates, and then subsidence. In case of Bangkok, I think subsidence is important. That means the sediment layers, the sand layers, are going down. And that's related always to a change in the groundwater level. And even if the groundwater at some moment stabilize, this sand will compact, we call, so it will compress together. And this can even go on for decades, even after the groundwater is not changing anymore. And then also we can use, of course, the GNSS. You see Captain Samart help us a lot with installing. And we have here actually also the GPS. So the GPS is measuring the absolute vertical motion, and the tide gauge is measuring the relative sea level rise. If we can combine both, we can get either the absolute sea level change, which should be the number the satellite is measuring, or we can combine also, I'll show you later, with the satellite, and then we have different ways to check and validate. Of course, the tide gauge, they're all around the coast, and I think they measured around 20 centimeters sea level rise, I think, over the last century. So that's already something which was going on anyway. But now, of course, it seems that things are accelerating because the warming up is going quicker. Okay, then the INSAR, that's not my expertise, but it can give you, like I told you, this change. This looks very nice. This is due to an earthquake. And this is the typical pattern, deformation pattern you get. This has to do with the fact that there's a wavelength you measure, you have to calculate. It's like the rainbow. When you pass from here to here, let's say that's 2 centimeter and 4 centimeter. That's a little bit, if you compare those radar images, what comes out of there. In case of an earthquake, but we're not talking about today. You can also look at the INSTAR can also be used to look at what, and then we look per pixel. So a pixel is the smallest resolution the radar can see. The same if you take a picture with your camera. Then the smallest dot in your camera, the Samsung or Apple, they say, yeah, we have 12 megapixels, so you have 1 pixel. So every pixel, and what you see below is this actually a city there. And then by combining a lot of those SAR images, you can get an idea what each pixel is doing. And here you see an arrow, red means here going down, and green to blue means nothing. So relatively in this image, where you see nothing, we don't get the data, because radar has to be reflected back, and a building is doing that fine, but for example, a rice field or an area with trees growing is not ideal for reflecting radar, so we don't get the pixels everywhere. But here you see an example where an area, this is a new area in development, is actually going down, and that has to do with groundwater. Groundwater level has changed due to urbanization, or sometimes it's also necessary to pump out groundwater for various reasons, and you can clearly see. So that's a very useful technique also to look at land subsidence. Again, this is relatively, so that means if the lowest, if they all are moving up by 1 centimeter, we will not see, we only see the difference. So in this image, I think this is 30 by 60 kilometers, we can see, I think it's a couple centimeter difference from blue to red, that the area is moving. Now, very quickly on the earthquake itself, I'm not going to talk about the tectonic setting. Of course, we are here in Bangkok, and Bangkok is quite stable area. If we talk about tectonics, you do have some earthquakes in north, in Chiang Mai, and in 2004, you all felt the big earthquake along the Sumatra Trench. And that one doesn't have a big impact directly on Bangkok, apart from you could feel the tremors, but it does have an effect on the motion of the land, both horizontal and vertical. And that can give an additional change in vertical motion, which might be relevant if you're looking how much the sea is going up, if you're going down. So this we call tectonic subsidence, okay? It has nothing to do with what people are doing. It just means the whole area or the rock below you is going down because of tectonics. And this is actually a cycle. So it's going up, it's moving over a period of time, and it's always repeating. You have a period in which nothing happened, everything looks fine. Then you have a period where there's a big earthquake. We call this the coseismic phase, and then we talk about the 9.x or 9.2 earthquake like we had in Sumatra. And then there's a period after the earthquake in which things are still moving differently as before the earthquake, and very slowly, they will start move like they did before. This we call post-seismic. And all of them have both horizontal and vertical displacement associated with it. Okay, you can actually see this here. This is all vertical direction deformation. This is a station, Chonburi, not a continuous station, but measured every year. This is actually measured by RTSD. And you can see before the earthquake, the land was doing something different vertically than after. And Chumphon in the south of Thailand, exactly the same. You see before we have, actually it looks like a little bit going up, but then after the earthquake, things are going down. The same you can see actually here in Phuket. The south has been much more affected by this post-seismic motions, also in the vertical direction. You can see Phuket was moving up before, and after the earthquake it was moving down. But this down motion is going slowly disappearing, you know. At some point, we don't know how long, it will start to move like it was before. This is the horizontal you can see, but that's not topic of today. You can see that before the earthquake everything was moving linear, but after it was not. But for sea level rise, relative sea level rise, we look at the vertical component only in the GPS. There's also some stations, actually this was, I think the red one is Rayong, closest to Bangkok. You can see after the earthquake, the first years of the earthquake, you see that in the vertical direction is going down. You also see a yearly signal, but this is a seasonal variation, and that's normal to see, and that's not really what we are interested in, but we are looking at a trend. So if you a line through this red, you can see it's going down. Okay. how important are those vertical motions? Of course, if you're interested in geophysics, but we're not talking about that, then they might also be related to post-seismic motions. This is actually a model based on, as a result of the earthquake, nothing to do with land subsidence from people, what people are doing. This is just from the tectonics, and then we combine the data. You can see that the prediction of the model was that the impact on Bangkok would be less than 10 centimeters. That would mean that after the earthquake, Bangkok, the whole of Bangkok could move down in the next decades, 10 centimeters additionally. So that's not a big number, but if you would build a dike, you might want to take that 10 centimeter extra in there just to be sure. And also, of course, the vertical motions, I already mentioned to you, you can use to look at what tide gauges are measuring and correct it from relative to absolute or the other way around. The land subsidence rates from INSAR is relative, but if you have a GPS point, 1 pixel with a GPS antenna, a GNSS antenna, you can make it absolute. So you can combine them. And the vertical motions, of course, they have a possible, well, we already know they have for sure a big impact on the relative sea level rise along all these low-lying coastal regions. And nowadays, there's many more people living there. Also, tourism, of course, going on. So let's look at the study case, Phuket. It's only one slide, but it will show you actually something which we also will do, or we are already doing, but we still have to do more on Bangkok. And then you see here that we make use of a tide gauge. You see here is a tide gauge. So this one is measuring the sea level. Actually, we also put a GPS on there. Then we have 2 points which have a GNSS. Or in this case, this is a GNSS station measuring more than just GPS. On this one, I think we measured mostly GPS yearly. This is at Promthep Cape. So we measure the vertical motion of the island with GPS, and at the same time, we measure what the sea is doing with the tide gauge. So of course, the tide gauge might be moving also vertically. So actually, what you see here is just the GPS measurement to all the years. Again, this is horizontal. We're not going to talk about that here. And then we have, but vertical is interesting. You see that before the big earthquake in 2004, the island was moving up. And then here, there's a sudden jump in the horizontal during the earthquake. In the vertical, it was quite small. I think it's hard to see. But what you see is after the earthquake, the land or the whole Phuket Island is not moving as it was moving before. But you see that it's moving down, so it's subsiding, tectonic subsidence. This station is located on bedrock, so there is no 1 or 2 kilometer sand there. So everything we measure is directly related to what the big rock or the crust is doing below. And then also, if we measure, so this is the GPS we have. You say I told you 3 techniques, actually 4. The one, but the INSAR, land subsidence, we are not using here because we have direct measurement of the vertical motion. And Phuket is a rocky island, so the land subsidence from sand layers is not a big factor there. Then what you see here is the radar, the satellite altimetry radar is also having a prediction. I think it was 3 point, I can read it better here. 3.8, I think, 3.6 millimeter per year is actually, it's measuring the absolute. Remember I told you the global one is 3.2, so this is 3.6, a bit higher, but this is measured by the satellite. The satellite just looks at the sea, so the sea around Phuket. It doesn't look at the land. And then here we see the tide gauge. The tide gauge actually is showing something quite funny. It was moving linearly, and then after the earthquake, suddenly this line is going up, which means it sees the sea going up much faster than it did before. But this motion from seeing the sea going up is again in time not going up as fast as it was initially. And this is exactly because the station was actually, the whole island was moving down. And so while the tide gauge is measuring the sea, it was also going down, because this motion, of course, is not changing over a couple of kilometers. It's similar it's representative for the whole island of Phuket. And then you could see actually here, if you would not have that information, you would not understand what goes on and maybe try to fit something linear. But you see there that it's important when you use the tide gauge, that you actually should know what the tide gauge is doing. It's by itself, vertical. Okay, so this you could do similar, of course, for Bangkok. And this is only one station. It's good to have more than one station because people could argue for some reason your data is wrong or something is going on. So let's look at now at Bangkok itself. Of course, in Bangkok, we have, like anywhere in the world, we have the threat of absolute sea level rise. The absolute sea level rise is the 3.5, 4. It depends a little bit on the studies, but it's all around that number that the sea is going up. So the whole world has to deal with. But regionally, this number can be sometimes a bit higher. So the ocean is not, the water is not uniformly distributed everywhere. So you have a global rate, but there might be some areas which are seeing the sea go up a bit faster, and even some areas where it's going to be lower than those 3 millimeter per year. Of course, we all remember the flood of 2011. So the flood, of course, came from rain, and the water came to Bangkok, and the water has to go to the sea. Of course, if the sea is getting higher and higher, it becomes, and also the land is going down, it becomes much more difficult to move all the water you get from the rivers, move it to the sea on time. If not, yeah, then you get, of course, the flooding because the water cannot be pumped or cannot go to the sea quick enough. So that always has a link, of course, with what the sea is doing. The sea is going up 1 meter, yeah, you're not going to be able to pump, I just exaggerate 1 meter, but you cannot be able to get rid of water 1 meter because if you pump it to the sea, yeah, and the sea is already at the same level, the water is going to come straight back, of course. Now, if you look at the satellite altimetry, so from here, of course, we have Bangkok. Then this shows you the trend, and this was based on a data set from, almost, this is 25, 26 years of satellite altimetry data. And this shows you that in the Gulf of Thailand here, the rate is around 4.5 to 5 millimeter per year. So that means that's what we, over all those years, what we have to take into account, what the sea is doing. So if the land is staying the same, each year the sea is still going up around 5 millimeter per year. You can calculate for 10 years, for 100 years, what that means. Apart from that, of course, we also have and that's also measured by the satellite, it's the cyclic annual behavior. And you have the sea in a period of time can be higher than another period, and that also can come, of course, from influx from more rainwater finding its way to the Gulf of Thailand. You see, actually, in the Gulf of Thailand, we have a quite big annual variation. It can be up to here, I think it's 20 centimeter per year. So at one point of the year, the Gulf of Thailand, the water can be 20 centimeter higher than it will be in another point. But this is cyclic. You have annual, this is the annual, you have semi-annual. But of course, this is also something you have to take into account, because if you're not lucky and the sea is already much higher, then for your sea level, it means that in this annual signal, you have 20 centimeter more water you're seeing along the coastal areas. Also, if you want to pump water away to the sea, and the seas again are temporary up to 20 centimeter higher, that already makes a difference. Okay, you see here, that's mostly the Gulf of Thailand. You see the Andaman Sea, we actually have less variation, and also I think the rate there is a bit lower. Okay, so that's the satellite altimetry. What it shows you, and we know, we can assume that those values 4.5 to 5 millimeter per year is still valid today. Of course, we keep on adding more satellite data. Then the first time I think we came here, we worked on this first project, we had an excursion to the Wat Kun Samat Trawat temple near Bangkok. And that one actually very well illustrates that, at least in this area, this is not Bangkok, but it's near Bangkok, there is a problem. You can see that the temple nowadays is, you can visit it, you can walk around here, and the monks preserve the temple. But if they have nice pictures there, and this, I think, the first picture is from 1970 or 19-something, the 60s. I think maybe you can see the year. But anyway, it's in time. And you see at one point the temple was actually inland. some distance from the sea. Then at some point the temple was already in the sea. And then later on it was already quite some distance into the sea. And nowadays, if you look back here, it's even much further into the sea. Of course, the temple has not moved away from the land, but the only thing which can explain this, because this rate is actually, if you look at it, how much it moved, it's, I think, for the temple, it's 1 to 1.5 millimeter. If you know the 3 millimeter per year, the global sea level rate, you can calculate back in the last century, that's never going to give 1 to 1.5 meter. So the only possible explanation for this one is land subsidence. So the land along this coastal area is going down. And of course, that means that the sea can take advantage of that and move inland. Because, yeah, if you move your land down, the sea will just get further into. And this is also visible if you look at all maps. This is an older map. You see the yellow dot is a temple. And then when you plot where the land and the sea is, because you get this data, this is also from satellites, we call this a digital elevation model. It gives you the height at every point, in this of course is Bangkok. And then if you plot the coastal lines from the 1970s, you already see that the coastal line here is also in the sea. So that also shows already that once, when they made the contour of the land originally, the sea was, and that's not that long ago, that some data goes back 15, 20 years, you know. So you clearly see, I mean, that there is something going down here. It's 25 kilometers away. So apart from this is a nice place to visit, but this is a very good example of what land subsidence can make it even more complicated for relative sea level rise or make the sea go up even quicker. All right. So what's all these possible causes? Because if you talk about that, you cannot just say that we have a big problem because this is the reason. No, you have to take into account all the possible reasons. So of course we can say that there's erosion of the low and flat slope of the central plain of Thailand. As I told you, the plain of Thailand, which is Bangkok is located, but it goes all the way to the north very far, is quite flat. And you can say that erosion from rain, the sand is flushing to the sea, so we are losing the land. But actually, it has grown by 70 kilometers in the past 6,000 years. That means 6,000 years ago, the sea was actually 70 kilometers more land inwards as it was today. So actually, the sea has lost from the land for a long period of time. But now it sees the sea is starting to win from the land again. So that erosion doesn't really make sense now. Okay, of course here I already put it in bold a bit, but sea level rise, absolute and or relative to land, I think that one is an important player. Of course, if the sea is going up and we also get more storms, then it's easier for the sea to erode the coastal region, flush away the sand, and you will lose the land. But that also doesn't explain why a whole area is slowly moving below, that you would see this progressive, each storm you would lose some of the sand. Of course, there are other ways, and there might be people even know more. There can also be a change in the sediment, the deposit of the removal in the river delta. But then again, I think that should not affect that much as you saw. But it's a possibility. But I will get, of course, into this one more. Another problem, of course, is the mangroves. They are the natural protection, and when they disappear or they are removed for construction purpose, of course, the sea has more free play along the coast. Of course, you have aerial pictures to see that, to see what happened. And of course, it also is important for a building is when you build it, how deep is the foundation of the building into the sand. If it's just on the sand, everything happened in the low sand layer, 1, 2 meter, 3 meter deep, the whole building is going down. If a building is on 20 meter deep pillar, then only what the sand is doing below the 20 meter is gonna make the building go down also. Of course, then as you can see in Bangkok, the land can still go down. You see the roads go down, but you see the buildings or the bridges, they are there. And then the door of the building was once at the same level as the road, and now the road has gone down by 10, 20 centimeter. We also see that in Holland, when, for example, we have a new area, we built houses, and then there was a swamp area, we have to pump away the water. Then you see for a period of time that the roads are going down, but the buildings are staying because we put them on 20, 30 meter deep pillars. Okay, so about this relative sea level rise on the West Bank River, I think that I already mentioned to you that there's a temple there, and we see something in there. Now, okay, this picture I showed you already earlier on. This is the earlier result made by Dr. Iti in the past, also in a project together. But if we look at tide gauges, there's 2 tide gauges here. Actually, there's many. This is Satahip. You cannot see on the map here, but you see the location. You know where they are, but they are not near to Bangkok. But those Bangkok Bar and Pom Prachun, they are. These are those 2 stations. Now, if you look at the tide gauge record, so the record from the sea height measured by then you see all of those, they show this trend. Actually, the blue one is also a Tapon is doing a little bit strange here, but let's just focus at this one. This is what you would get if you have this couple millimeter per year global sea level rise. But those 2 stations here, and when they started, here actually you see a jump, but this is a change in the datum. That means the vertical reference was changed because and then you sometimes get these jumps. You also see it here. But let's just focus in this area. You see that it's much steeper actually moving up. And that's measured by the tide gauge. So the tide gauge see the sea going much quicker up than the satellites or the global rate is. And that, of course, means that that those 2 tide gauges themselves, they are moving down into the sand or along with the sand. And that's why they see these much higher rates, I think 13, 15 millimeter per year. I think we did a reanalyze, I'll show in the next slide, we even got 18 millimeter per year for that tide gauge. So that's much higher than the 3 millimeter per year, okay? Important to know here, and that's also for the study something, is that tide gauges or building or even GPS, GNSS stations, they are on buildings which are built on pillars that go XX, because we don't always know, meter deep. Okay, so and they create this severe land subsidence, as you see here, because those ones, they have nothing to do with the global warming. So from the tide gauge, we get up to 50 millimeter per year. Yeah, we can get relative sea level rise near Bangkok. Actually, this one is already situated in Bangkok. Okay, that's a number just to remember. And also people, just to confirm about the loss of the coastal lines, I think there's also Thai scientists who looked at the coastline, and you see that the coastline here is clear loss of the coastline through all the years. So something is going on there. And what's going on? Erosion, I think, would not explain why this area would be going down much quicker than other areas. But that's just to show that it is really happening. We cannot deny it's happening. We can discuss on the reason behind it, but it is happening. Okay, so in the Bangkok area, we did a more analyzed look at one tide gauge we have at the naval dockyard. We got for which data is available. The top picture is a satellite altimetry, so just a satellite looking down on the sea around Bangkok. And it's not influenced what anything is going on land. It's just looking at the sea. So you see that there's a rate going up. I think it's 4.5 millimeter per year we find for the data period, which is similar to the 5 millimeter you saw in the other plot. Now for the tide gauge, we see a period where we actually see 80 millimeter per year, but then suddenly we have a jump, and then the next phase, it looks since 2004 that there is no sea level rise anymore. Although there is 3 millimeter per year, we know from global, but the tide gauge is not registering it. And then actually you have to look more into detail what could be the error source. It's not just processing the data, because you could do that, but you clearly see something is wrong here. Now on the bottom is the GNSS. We put the GNSS on there since early 2013, I think it started work properly. And you can see it also measuring. And it's measuring about -2 millimeter per year. So it's seeing some subsidence. But the antenna is on a pillar up to, I think, at least 20 meter. So that means the 2 millimeter per year going down is for the sand below the 20 meter. We don't know what's going on in the first 20 meter, because that's the foundation on which of the dockyard. And we put the antenna on that. So is the tide gauge. But here what actually happened is that the tide gauge was moved. Before, I think it was on land, and it was not on a 20-meter pillar, but we have to really find out more information about that. And then it was moved to the pier, and the pier is on this very deep, at least 20-meter deep foundation. And so the tide gauge is suddenly only measuring what's the signal is below. But then still, you can combine, actually, the satellite altimetry. I think this was 4 to 5 millimeter per year. Then you can intercombine. That means you can combine the different measurements with each other and to see if it makes sense. If the sea is going up by 4 millimeter per year, and the tide gauge is also measuring 4 millimeter per year, then you subtract. That means that the GNSS should measure 0 meter or no vertical measure of the tide gauge station. And this is how you can intercombine also different techniques. But in this case, apart from the first period of time, if we would extrapolate this area and combine with that one, it makes sense. But here you see there is some area, and there is some problem here because the tide gauge should still go up a little bit more here. But probably we have, again, a vertical datum problem. Okay, land subsidence results. That's a result we've done in the project by Dr. Anna Aopat. Anapo, his first name is familiar. We did the work. And this shows you that there are areas in Bangkok where you have clear subsidence, and the subsidence here. This was not the latest result, but I think up to 30 millimeter per year, we see that some areas of Bangkok are moving down. Not all of Bangkok, but relatively, okay? So that means if all Bangkok is going down 1 centimeter per year, then actually it would be 10 millimeter per year, it would become 40. I cannot read what it says. 10 minutes, 10 hours. 10 minutes I should manage. Okay, so that's the INSA result. Okay, just remember from that up to 30 millimeter per year relative land subsidence. Now let's look at the GNS data. We have a number of stations already operating for a long time. Actually, the longest one we have, although we have to combine 2 nearby stations because the BNKK station stopped operating at some point. And then we put a new station at the Royal Thai Survey Department Survey School. It's near the Ratchaderm boxing stadium, and we have it since 2005. And that's the horizontal, not talking about that, but we look at the vertical. And you see here that actually up to a certain period of time, I think we have a subsidence rate here around 5 millimeter per year. Then that's, okay, this is a combined, and this is, if you only would look after these years, it's a bit lower. Then we have the station. This is the national station at Chulalongkorn University on top of a building, a high building, so the pillar also must be quite deep, but there we have minus 2.5 millimeter per year vertical subsidence. And then at the dockyard, I showed you in the previous slide, we measure around 2 millimeter per year. But they're all minus, so they are vertical motion, they are different patterns, but they all show land subsidence. Of course, they only measure what is happening below, how deep the foundation they are on. And I think this is 20 meter. This one maybe 20 meters. So in the first 20 meter of the sand layer, we cannot, we don't know. The GPS will not see it. But yeah, the road can still go down. Okay, so the ideas, findings of the coastal land erosion. So it's clear that the relative sea level rise appears to play an important role here. Land subsidence has been 1 meter or more in between 1960 and 2020. The absolute sea level rise, so that's due to the global warming or the global change, only contributes 15 centimeters. So we have a gap here in this area. You know, you can calculate 1 meter minus 15. So that has to come from the land subsidence in that area. That's one area. It doesn't mean that the whole of Bangkok has moved 1 meter down, but at least in some areas that happened. Of course, I think the mangrove deforestation, that's another topic. It will result in a quicker loss from coastal areas. And why that happens? Yeah, that happens in many development or industrial. The city is growing, so sometimes nature, exactly the same in Europe, has to move. Until nowadays we try to change it around because, yeah, but that can have an impact also. And of course, another reason, groundwater pumping now in the past, I think, might also, of course, be a big factor because it makes the sand going down if the groundwater level is moving down. Okay, so now we're almost ending. Now let's look at a possible relative sea level rise scenario for Bangkok. So there are different measurements we could, as I explained to you before, what techniques we can use. We have 3-4 different techniques which we combine. But from that, let's just not exaggerate and not to make numbers which makes no sense. But let's say the sea level rise, the relative sea level rise is 1 centimeter per year. That means if I'm standing here, then in Bangkok, I see the sea go up 1 centimeter per year. And that comes from the 5 millimeter per year, which I show you from the satellite altimetry, and 5 millimeter per year land subsidence. I show you that some areas in Bangkok have up to 3 centimeter per year. But from the GPS, we get to 2 to 5, so 5 millimeter is not an exaggerated number. So that makes 1 centimeter per year. Now we can just take a digital elevation model of Bangkok, and then we can adjust the sea, the mean sea level through the years, and then actually you can get something like this. So this is the present status, and here I do it quickly. We move by, I think by periods of 100 years. So that means we change the sea level because the land is going down, and you see what's happening already. If you would do nothing, you see that, yeah, indeed, Bangkok will become mostly, well, not all in this up to that point, but large areas start to become underwater. Okay. To do that a little bit better, I hope this one works. That is already something we did years ago, but it's still a very, very nowadays. I think it really makes sense. It's the same. We only assume 1 centimeter per year, and then we're gonna see. If we don't do anything, then this is the Bangkok plain, this big area, which has a very slow slope, so the height of the land is going up very slowly here. What would happen if not there? Yeah, here you see the mean sea level increase, and then I think we're going to do it for... Yeah, and I must say, that, my colleague put some music there, so you don't panic, you know, so he put some nice Thai music there to relax. So this is just a simulation, okay? But you will see the time here going up to the year 3000. And actually, yeah, we have all the provinces here. And I numbered actually the provinces which will be flooded first. So if you have land, you might decide to move to the other land. But just this is just an idea what would happen if progress. You can very clearly see if nothing happened. If nothing is done and the sea keeps on, this actually assumes the sea is not going up quicker. If it warms up more, the rate might even go up. But that if nothing would happen, and you see here, this is meters, 1 meter, 2 meter, 3 meter, 4 meter, 5, 6, 7, 8, 9, 10 meter change. That would result in this whole area being reclaimed by the sea. Actually, it was, as I showed you 6,000 years ago, a big area was actually. So, and that's actually, if nothing would happen, of course, 3,000 years is a long period, the year 3000, but it just shows you if you don't do anything, then for sure you will get a problem. Not only Bangkok, of course, and some areas are even worse. Okay, this brings us to the conclusions. Absolute sea level rise due to climate change is undeniable, and satellite altimetry shows Bangkok is facing a rate up to 5 millimeter per year in the Gulf of Thailand. Whether this is a threat is depending on what the land is doing. So firstly, the GNSS shows absolute subsidence rates up to 5 millimeter per year in the past 25 years. The INSAR shows relative land subsidence taking place within Bangkok at rates up to 3 centimeter per year. That's data about 15 years. We can look at since the satellites are available. The tide gauges, they have much longer history, show relative sea level rise rates up to 15 millimeter per year in the past 60 years. So that's the combined effect, of course, of sea level rise plus land subsidence. And then having those multiple techniques, that makes the science case stronger. You can make combinations between the different techniques, either to calibrate or validate to get even more better insight in that. Okay, and then there's a small one, I touched that very briefly, tectonic subsidence components also, which might, but that's not that big, that might create 10 centimeter additional subsidence. Yeah, and of course the groundwater production, or if groundwater level changes and sea level rise together, they increase, of course, the flood risk in this area. Now the outlook, and that's the last sheet, It is clear that the relative sea level needs to be continuously monitored to get awareness of its possible threat to Bangkok. That's also once, I think some of you might already show some of the material before. We have to make the people also aware, but of course give good information, not create panic, because you see, if you don't do anything, the first couple of years you get more floods, but it's not going to be Bangkok below the sea in 5 years or something. You know, that's not going to happen. Of course, if you wait longer and longer, yeah, it might happen. Okay, so tide gauge and GNS data, and there's more agencies operating GNS, but they don't go all that back that many years. And the longer they go back, of course, the better. But it's good to continue that. And also to use all the available satellite altimetry. That's no problem. Everybody can get that for free. It's a database which are available. Of course, and INSAR data, nowadays, the satellites, I think ESA is also doing it, and the Japanese are now making the data free, so you can get all those images for free. Of course, you have to process the data still. The cooperation itself between ourselves and many Thai agencies and universities started a long time ago. It's still ongoing, but for sure it should be extended with more Thai partners. And thereby, of course, for research, still we have to measure data travel to do that, both within Thailand, you know, or if you want to exchange results. So that's also something, of course, which is also important to get funding. So all the funding we get is actually always for research, and yeah, that means that every baht we get goes really into research, of course. Now, today we talk about countermeasures, but unfortunately, science cannot directly provide countermeasures. However, it can provide, and I hope I convinced you about that today, reliable measurements which can be used as input to the measures itself to be taken in order to prevent Bangkok from otherwise gradually, it's not going to happen in 5, but very slowly if you do nothing, gradually really becoming an underwater city in the future. But for Bangkok, I think there is still time. Jakarta is a much bigger problem already. So, but yeah, at least I hope the science provides you with the good data. And then later on, as you will get in the discussion today, you will hear the response from all the other authorities or disciplines which have to try to tackle that in the near future. Okay, that's it. Maybe I took 2 minutes more, but that was my talk. Thanks a lot for your attention.